And the thing about the second derivative test that always gets students, because we've already learned the first derivative test. The first derivative test is where you made that sign diagram to show where something's increasing and decreasing, then increasing again. And if something goes increasing then decreasing, you have a maximum. If something goes from decreasing to increasing, you have a minimum. So the first derivative test helps you find out if things are maximums or minimums or stationary points of inflection just by looking whether the original graph was increasing and decreasing. Okay? The thing about the second derivative test is we've learned that the second derivative test tells us about concavity. So the main thing that people get confused on with the second derivative test is they think it's for concavity. So make a little note here. The second derivative test is not for concavity. It's not to find out if it's concave up or concave down. The second derivative test is an additional test to tell if something is a maximum or a minimum. So it's in addition. You already have a way to find out if something's a maximum or a minimum, and now we're showing it in a different way. Okay? So what the second derivative test says is if we find that on our first derivative it's equal to 0, a critical point, and then we find out on our second derivative that it's greater than 0. In other words, when your second derivative is greater than 0, you know it's concave up. That means it has to have a minimum. So a little explanation based on what we've done so far. If you found your first derivative test and found out that at x1 it was equal to 0, you would do your number line. Normally then you would do your arrows, but let's say for whatever reason you didn't do your arrows to find out that it's a minimum. And then you did your second derivative. You drew that line. Maybe there's a point C where the second derivative was equal to 0, but you still had x1 on here. And at x1, it's concave up, and the first derivative is equal to 0. The only possibility then is that it would be a minimum. Now, generally, students never use the second derivative test for minimums because you would have done this sign diagram. You would have used your first derivative to say it's decreasing, then increasing, so I know it's a minimum. And then we forget about the second derivative test. However, there are some IB exam questions where they just give you little bits of information. So they would give you that f prime at 3 is equal to 0, and f double prime at 3 is equal to 27. What can you tell me about 3? And from that, you would be able to say it's a minimum because it's concave up and because the first derivative is equal to 0. Same thing if the first derivative is equal to 0 and the second derivative is less than 0, meaning that it is negative and concave down. The only possibility if the first derivative is 0 and it's concave down is that you have, and did we change it in your notes? Because on mine it still says minimum here. It should be maximum at that point. So what does this look like with some questions? Use the second derivative test to find stationary points for the following functions. Again, it's always good to use your previous skills to think about a situation. This is a positive x cubed graph. So from grade 12, you might already have this shape in your mind. And if looking at that shape, it appears that it could have a maximum and a minimum. Okay? If we're finding the second derivative test, the second derivative test needs two things. You need to find out where f prime of x is equal to 0, and then find your second derivative and check those points to figure out if it's increasing, if it's concave up or concave down. So starting with our first derivative, the nice thing about curve sketching is all the derivatives are fairly easy. We find our first derivative, set it equal to 0. We can factor out a 3x. And we find that our first derivative is equal to 0 at 0 and 2. So we have two possibilities for maximums and minimums or stationary points of inflection. Now normally, and I'll just put it down here, normally you would draw your line here, because once we get to full curve sketching, this is what you would do. You would label those critical points of 0 and 2. Remember, on our number line, we also label non-permissible values, but in this case, there are no non-permissible values. So the only critical points are 0 and 2. And now I'm going to skip a step that you're going to do next, usually, is where you would find out if it's increasing or decreasing in those sections, because we're using the second derivative test. Next, if we find our second derivative, so we take our first derivative, 3x squared minus 6x, find the derivative of that, we'll get 6x minus 6. Here we have our second derivative. Now, normally, on curve sketching, to find your inflection points, you would set your second derivative equal to 0. Okay? So I'm going to do what you would normally do in a situation like this. Set that second derivative equal to 0, move the 6 over, and label where your second derivative is equal to 1. Now, we don't need all of the information to find out, is 0 going to be a maximum or a minimum? So using the second derivative test, at x equals 0, we know that f prime of 0 is equal to 0. We know the first derivative is equal to 0 at 0. What is the second derivative at 0? It's equal to negative 6. So we can say, and this is a statement you would need for your second derivative test, since f prime of 0 is equal to 0 and f double prime of 0 is less than 0, the graph is concave down at x equals 0, and we have a maximum. That's the second derivative test. If the first derivative is equal to 0 and the second derivative is negative, you know it's concave down. And the only possible way to have a horizontal tangent, because that first derivative equal to 0 means our tangent would be horizontal and concave down, the only logical thing then is a maximum at that point. Okay? We can do the same thing for at x equals 2. We know that f prime of 2 is equal to 0. We can go to our second derivative and plug into 6x minus 6. Our second derivative would be positive. And we can write the same statement. Since f prime 2 is equal to 0 and f double prime of 2 was greater than 0, therefore concave up, we have a minimum. And now I'm going to fill in what's going to happen normally when we curve sketch and do everything together. Because I left some things blank. I didn't do the first derivative test because it would ruin the second derivative test's surprise. Not that that was that exciting of a surprise to find out if they're maximums or minimums. But if we look back at the whole question in its entirety, wow, that's too small. I'll just zoom back up. So first of all, we already knew what the shape looked like. Did it match up that at 0 we had a maximum and at 2 that we would have a minimum? Does that make sense with what our original graph looked like? Yes. Okay. We found our first derivative and where it's equal to 0. What we didn't include is the first derivative test. In the first derivative test, you would take a point less than 0. You would plug that into your derivative and find out that that would be negative. No, find out that it would be positive. Like -1, you'd have a negative number here and a negative number there. Multiplying together, those would be positive. And then between 0 and 2, you'd plug in a number like 1. This then would be a positive factor. 1 minus 2 would still be negative. This section would be negative and decreasing. And finally, plugging in a number larger than 2, like 3. This is positive. 3 minus 2, this is now positive. Positive times a positive is positive. So your first derivative test tells you at 0 it's a maximum, at 2 it's a minimum. Our second derivative tells us about concavity. We know that at x equals 1, we have a point of inflection if it changes concavity. Remember from the second derivative, just showing that something's equal to 0 does not mean for sure it's going to be an inflection point. But now if I plug into my second derivative something less than 1, like 0, I'll get negative, telling me this whole section is concave down. And if I plug in something bigger than 1 into my second derivative, this whole section is positive. Going back to our original picture, what we just found x equals 1 is this point right there. And this section of our graph is concave down, and this section of our graph is concave up. So the blue is what you would naturally do when curve sketching anything. You sort of go through a process, find your first derivative, find your critical points, draw out your first derivative test. Okay? And then find your second derivative, find your critical point, figure out your concavity. Okay? Now, because this is the natural progression, once you've done this sign diagram with your arrows, you know which are your maximums and minimums by your first derivative test. And so students rarely use the second derivative test to find maximums and minimums because it's already obsolete by the time you get to that point. Okay? So that's why I'm making a special note to say the second derivative test is not about concavity. The exam sometimes likes to ask specific questions to see that you understand that. And so the second derivative test, which we wrote out in words here, says if your first derivative is 0, and you know the concavity at that point, then you can find out if it's a maximum or a minimum. So we're going to do the second derivative test for this question as well. It's a positive x to the 5. So you might recognize that it's something like that maybe. Could have a couple maximums and a couple minimums. It doesn't have to look like that, but that's a general shape of an x to the 5 graph. So using the second derivative test to find maximums and minimums. Our first derivative, set our first derivative equal to 0, we can factor out a common factor of 15x squared, leaving us with the difference of squares. And 3 critical points. So normally at this time you would draw your number line, you'd plug in 0, -1, and 1. But we're going to skip the increasing, decreasing so we don't spoil the surprise. We have no non-permissible values, so you wouldn't have to add any extra points to your number line there. Our second derivative (60x cubed minus 30x). Again, set your second derivative equal to 0. You can factor out a 30x. Ooh. Do you want to have some fun? Is this a this isn't a difference of squares, right? If you were solving this equal to 0, I'm guessing most of you would say this is equal to 0, so I'll move my 1 over and divide by 2 and get x squared equals 1/2, and then square root both sides to solve that. Do you think that's how you would probably do that? Yeah? Okay. Now, just for fun, you're allowed to bend the rules a little bit sometimes. I'm going to factor this as a difference of squares. Is it a difference of squares? Not really. Because is 2 a perfect square? No. But if you wanted to, what times what is 2? Root 2. So you could write root 2x and root 2x plus 1 and minus 1 and bend the rules a little bit. Can you see that this one would give us -1 over root 2, and this one would give us the +1 over root 2? It's the same answers that we did by the square rooting before, but just looking at something differently. So in our second derivative, we have 0, -1 over root 2, and 1 over root 2. Now for testing your concavity, and I'll put where things are concave up and concave. No, I'll leave that, so we don't want to ruin anything. We'll go right to our second derivative test, then we'll go back and fill in the things we would have normally done. So normally next you would check each of those to find out where it's concave up and concave down. But for the second derivative test, we need to check at, our first one was x equals -1. Okay, at x equals -1, we know that f prime at -1 is equal to 0, and f double prime at -1 is, so now we're going to have to plug in -1 into our second derivative. We would get -60 plus 30, which would be -30. It's concave down, and we have a maximum. at x equals 0, we know that f double prime of 0 is equal to 0 and, sorry, f single prime and f double prime is equal to 0. There is nothing we can say yet about maximums or minimums from the second derivative test here. It looks like it's going to be a stationary point of inflection. So we can't use the second derivative test to say anything about 0 because the second derivative test is only helpful if the second derivative is positive or negative. Yeah, I'll put 0 in there. Thank you. So we'll write that it is going to be a stationary point of inflection. But here's where our second derivative test causes some problems. In our first derivative test, where we would see at that point that it either stays increasing or stays decreasing, that would imply that that's a stationary point of inflection. And at x equals 1, f prime at 1 was equal to 0. F double prime at 1 would be 60 minus 30, which is positive 30. Meaning that it's concave up. And we would have a minimum. So if the first derivative is 0, that means your tangent is horizontal. And if it's concave up, the only way that you could have, and I like drawing a little picture of concave up, it's really easy to see that it would be a minimum there when you draw the picture, rather than trying to memorize it. Just draw the picture and it becomes obvious. Now what's missing in this question? If we would go back and fill this in, we would have found out that before -1, it's increasing. Then at -1, which we already found out is a maximum, after that it would have to be decreasing. It stays decreasing between 0 and 1, and then goes back to increasing after. So your first derivative test would have told you at -1 you have a maximum, at 1 you have a minimum, but at 0 your original function stays decreasing, so you would have an inflection point and a stationary point of inflection. So from your first derivative test, we would know that our graph goes up, has a maximum, flattens out but stays going down, and then goes up again. Here's -1, here's 0, here's 1. From our second derivative test, if we plugged in values into our first derivative here, we would have found out this section is concave down, this section was concave up, this section is concave down, telling you at 0 it is an inflection point. So then you would know for sure that that would be a stationary point of inflection at 0, and then back to concave up. If I go back to my little sketch here, the points that you would have found with your second derivative would have been these 3. And you have concave down here, concave down there, concave up here, and concave up here. So you can see the different sections of the graph. What is this all leading towards? What we're doing right now is exactly that, sketching that graph perfectly. Okay? We found out where we can have maximums and minimums. We found out where the x coordinates are for inflection points. For graphing it completely, all you would need is to add the y coordinates. And when you're trying to find the y coordinates of your original graph, you plug your x values back into the original equation. So the confusing thing about curve sketching is where you plug in your x values. Because sometimes you're plugging x values into your derivative, and sometimes you're plugging x values into your second derivative, and sometimes you're plugging x values into your original equation. Those are the three situations that you have. When you plug an x value into your original equation, you get a y value that's a point on your graph. When you plug an x value into your derivative, that tells you where things are increasing and decreasing, and that's just for this sign diagram. When you plug in x values into your second derivative, that tells you where it's concave up and concave down. So to find a point on your graph, you're always going back to your original function. All right, now let's get to some messier ones. All right, so we'll write down our first derivative and write down our second derivative. And one of the things that you see in the first derivative is that there was a common factor of e to the x, and that could get factored out in front. Okay? And with the second derivative, again, you would have another product rule here when you're doing your derivative. Derivative of, keep one the same, derivative of the second, then keep the second one the same, derivative of the first. And once you've done the second derivative, again, there's a common factor, and that can be factored out. So taking that information, we can find out where is our first derivative equal to 0. And since e to the x is never 0, the only place your first derivative could equal 0 is when x plus 1 equals 0 or when x is equal to negative 1. Why is e to the x never equal to 0? One of the ways and one of the things that we always have done all the way through is graph. Probably the thing you find, would you say graphing is one of the more annoying math things you have to do? Yes. Takes so much space, takes time. Your answer is this big graph. It's not like this nice feeling of a solution, x equals 3. But the graph can really help you see this. Because what does an e to the x graph look like? It's an exponential graph with an asymptote at y equals 0. Is it ever equal to 0? No, because it has that asymptote at 0. So one of the things that we learn as a skill throughout our math classes is that having the graph as another way of thinking about it can help us visualize and get an answer sometimes quicker than thinking about it algebraically. And so if we can use all of these tools, algebraic and graphical, as we go along, we have a better understanding of what's going on. So we have that at x equals negative 1, we have some sort of stationary point. Then if you plug in negative 1 into your second derivative, your second derivative, you get e to the negative 1, which is 1 over e, times 1. This is positive. Draw your cyclops, positive, concave up guy. And you know that it has to be a local minimum. So I want you to try the next one. I'll put up the derivative and the second derivative. Again, just try the second derivative test. You don't have to go through everything. Okay, so just find your first derivative where it's equal to 0. Find your second derivative if it's concave up or concave down at that point to say if something is a minimum or a maximum. Here is a check for D to see how you did. You have a local max at 0, 1. And let's finish up with the last question here. So we've got an x cubed graph. Part of the graph is shown. There is a maximum point at M and a point of inflection at N. So this is an old exam question. Find f prime of x. Well, that's a straightforward derivative. No problem. Find the x coordinate at M. So if we factor and set our first derivative equal to 0, we get two factors. And since we already know the graph is shown to us, I know that the first number, or the number to the left, x equals -5, it has to be at M. And this point over here is where we would have 1. Because of the way the graph is given. You don't need to do any extra math to show that it's a maximum there because they've given you enough information to tell that. Find the x coordinate at N. Well, that's a point of inflection, so we would need to find our second derivative. And set it equal to 0, so we find out that N is at -2. The line L is the tangent to the curve of f at 3, 12. Find the equation of the line in the form ax plus b. So this is going back to finding a tangent of a line that we've done before. What do we know? We know the slope of your tangent is always from your first derivative. We've figured out our first derivative to be x squared plus 4x minus 5. We can plug in 3 and find out our slope is equal to 16. So way back in grade 10, you learned that the two important things you need to find an equation of a line are slope and a point. We now have the slope. The point was given to us in the equation. So we can plug it into the point slope form or into y equals mx plus b, rearrange, and get y is equal to 16x minus 36.